Welcome back to the first course in general physics, and in this lecture we will be discussing the last part, the fifth part of the subject, dynamics of a particle. In this lecture we will continue talking about the potential energy and finally reach the principle of energy conservation, the conservation of mechanical energy. So in the beginning we will talk about work and potential energy. We will continue from the last lecture talking about this topic until we have covered it in a systematic manner, and then we will define the other kind of forces, which are the non-conservative forces, forces that do not conserve mechanical energy while they are acting and doing work on the object. And then we will talk about how to calculate the potential energy from known principles and developed methods previously. Then we will discuss the mechanical energy of the system. We will define the mechanical energy, and we will arrive at the conservation of mechanical energy. We will then evaluate the work done by a non-conservative force. We will develop methods and know how to calculate the work done by non-conservative forces. And by the end, we will relate this work and the work done by conservative forces, the mechanical energies, in a global statement, which is the principle of conservation of total energy. In the beginning, we will continue from last lecture. In the last lecture, we have talked about the potential energy and the relation of that potential energy to the work done by a conservative force. We have to remind ourselves that the concept of potential energy is associated with the concept of conservative forces acting between the different parts of a system. So whenever we say that we have a conservative force, that means we can always derive a function that is the potential energy, that gives the potential energy of the system, or vice versa. If we have a function that gives us the form of the potential energy of a system, that means we can always derive a form or a formula for the force, the conservative force in this case, acting on the various parts of the system. So here we have to remember always that the concept of potential energy is intimately related to the existence of a conservative force. Each conservative force is associated with a potential energy. And when this conservative force is acting, it is actually an interaction force. If the system consists of two objects, we say that the first one acts by F1 on the other, on the second one, and the second one acts by F2 on the first one. And it is always a force of interaction. So whenever we look at the work done by the conservative force, as we have discussed earlier in the previous lecture, we have the difference in the potential energy of the system, and we insist that the potential energy belongs to the system. It does not belong to only one object of the system. It belongs to all the system as a whole. So the work done on any part of the system is related to the energy difference of the system by the relation, the change in potential energy of the system due to the work done by a conservative force is equal to negative the work done by the conservative force. And that we have demonstrated by looking at the work done by the gravitational force, which is a conservative force. And we mentioned the example that if we toss an object upward, the object will start with a given speed, and it will slow down as it travels upward due to the work done by gravity, because the force of gravity points downward, and if the displacement of the object is upward, that means the work of gravity is negative. That means the work would act in such a way to decrease the kinetic energy or to transfer kinetic energy from the particle that is traveling upward. And as we said, where does it transfer this energy to? Where does this energy go? Because the energy is conserved. Since we know that if the particle goes down, back down after it comes to a momentary stop, if it reaches the initial position, it will gain back its kinetic energy, the same energy that it had before, which means that there is no energy loss. So when it goes up, it loses kinetic energy. Where does that kinetic energy go? Because energy is conserved, this kinetic energy is transferred to another form of energy, which is the potential energy, as we said, and this potential energy is associated with the work done by gravity. So as the kinetic energy decreases as the particle is going up, the potential energy increases. The configuration or the arrangement of the object relative to Earth, which is our system in this case, is changing, which leads to a change in the potential energy. So this is the relation between the potential energy and between the work done by a conservative force. These key issues are important to remember. Now, if that's the case for the conservative forces, that when they do work, they transfer energy from one form of mechanical energy to another form, from kinetic energy to potential energy, or back from potential energy to kinetic energy. That's the work done by conservative forces. What about other types of forces in nature? Do we have other types? Indeed, we do. We have forces which do not conserve energy, which means if these forces act on any part of the system will lose energy. And if we bring the system back to its initial configuration, we will find that the total mechanical energy of the system, or the kinetic energy of the system, has decreased from its initial position, from its initial value. So in these non-conservative forces, the kinetic energy will be transferred into another form, or transformed into another form of energy, which we can call it thermal energy, for example, and the mechanism by which the kinetic energy is transformed to this other form of energy, which is thermal energy, is the work done by the non-conservative forces, W sub NC. NC goes for non-conservative. So, as we said before, doing work is the process by which energy transfer occurs. So, if the force is non-conservative, the energy is transferred from mechanical energy, from kinetic energy, to another form of energy, which is thermal. And thermal energy is not a potential energy. The transfer of energy, this transfer of energy due to the work done by non-conservative forces, is not reversible. And we can understand that by taking a simple example. For example, if we push an object across the surface of a table, frictional forces act on the object as it travels on top of the surface of the table. And this frictional force will reduce the kinetic energy of the object as it moves on top of the table. And there is no way that this energy loss is retrieved. There is no way by which we can obtain this lost kinetic energy again, because this loss in kinetic energy has gone into another form, which is heat, thermal energy. Thus, if we have a precise probe, we can notice that after the object has traveled across the surface of the table, the temperature of both the object and the table has gone up due to the fact that it had gained some thermal energy. And that thermal energy has come to the system from the loss in kinetic energy. But there's no way that we can transfer the thermal energy back into kinetic energy. So the process is not reversible. Frictional forces, thus, are non-conservative forces. So if a frictional force is acting on an object as it moves, the object loses kinetic energy, and there is no way to retrieve it back, as we said. And the thermal energy that the frictional forces produce is not a potential energy. It is not a form of energy that is mechanical, that is stored in the system, that can be converted back into another form, which is kinetic energy. There is no way to do that. So, thus, potential energy is not associated with such a force, which is the frictional force. There is no form of potential energy associated with the frictional force or the work done by the frictional force. These forces are somehow called dissipative forces, where when they act on the system or on part of the system, they lead to loss in the mechanical energy of the system. Thus, we conclude that the work done by a non-conservative force would entail or lead to a waste in mechanical energy. A system with a certain amount of mechanical energy, potential plus kinetic, if acted upon by a frictional force or any other type of non-conservative force, will suffer from a reduction in this mechanical energy that it had initially. So far, we have talked about the potential energy and its relation to the conservative forces, to the work done by a conservative force. And now we have the tools, the right tools and the key points which we can use in order to calculate the potential energy. So if we have a force of interaction between different parts of a system, and the system interacts via conservative forces, these conservative forces have a potential energy function associated with them, as we mentioned, which can be calculated from the work done by the conservative force. So calculating the work done by a conservative force would give directly the potential energy with the relation between the two given by the change in the potential energy of the system is simply equal to the negative of the work done by the conservative force of interaction between the different parts of the system. And what we mean by this is, for example, if the system is Earth and a ball moving, a football, for example, moving in the field of gravitation, of Earth's gravitation, then the system is the ball and the Earth. This is our system. The force of interaction between the two is the gravitational pull on each one of them. So Earth pulls the football by a gravitational force which is equal to the mass of the ball times g, the gravitational acceleration, and the force points down. Equivalently, by Newton's third law, the ball pulls on the Earth by an equal force and opposite in direction. We can, of course, see the effect of the Earth's pull on the ball, but we cannot see the effect of the ball's pull on the Earth, because the Earth is so massive, so we cannot detect the effect of the pull of the ball on the Earth itself. But we can detect the effect of Earth when it pulls other objects which are small, because the response would be obvious in that case. So this is, as we said, the system in this case is the Earth and the ball, and the force of interaction that we mentioned is the gravitational attraction force. And this force is, if it is a conservative force, then there will be a potential energy associated with this force. And we will learn how to calculate this potential energy from calculating the work done by that conservative force. In order to do so, we use the definition delta U equals minus W, and we use the previously developed methods for evaluating the work, because we have learned previously how to calculate the work done by a force if we know the force. And by calculating the work done by the force, we can calculate the change in the potential energy. And by taking a standard value for an initial potential energy, then we can evaluate the function which determines the potential energy at each position or at each configuration, at any configuration of the different parts of the system, as we will learn in a little while. For example, let's consider the work done by the gravitational force on an object that is moving under the influence of gravity. The work done by gravitational force was calculated previously. So in this figure, if we consider an object of mass m that is moving under the influence of gravity, if the object moves a displacement delta y, we are concerned only with the vertical displacement. As we mentioned previously, if an object moves sideways across horizontally, the work done by gravitational force as the object moves horizontally is 0. So the work done by gravity is only non-zero if the component of displacement which is in the vertical direction is non-zero. So in that sense, we consider only one component of the displacement when we are considering the work done by gravity, which is only the vertical component of the displacement. This is the only component that gives non-zero work because the angle is not 90 degrees. The horizontal component has a 90 degrees between the displacement and between the force, which gives a 0 work. So that's why we are considering only the delta y. Thus, the work done by gravity is simply minus mg, which is the weight, that's the force of gravity, times delta y, which is the displacement, the vertical displacement of the objects. That's the work done by gravity. Let's check this statement. Suppose that delta y is positive. Delta y is positive. That means the object moves from a point, an initial point, to a point that's higher than it. So the final point is higher than the initial point. In that sense, delta y is positive, and the object is going upward. So delta y is positive, and the object is going upward. Now, the displacement is upward, the gravitational force is downward. That means the angle between them is 180 degrees, and cosine that angle is -1. That means the work of gravity must be negative. So let's go to the formula. Wg, the work done by gravity, is equal to minus mg delta y. If delta y is positive, g is positive, it's the magnitude of gravitational acceleration, and m is positive, which means that the total, the sign of the right-hand side is negative, because we have a negative sign multiplied by everything that is positive, which means that the work done by gravity, if the particle is traveling upward, is negative. And that is true from logical consideration and from the treatment that we have done previously. Now, similarly, if the object is traveling downward, then the initial position, y initial, is higher than the final position, y final, in which case delta y, which is y final minus y initial, is negative. If delta y is negative, then we have in the formula for calculating the work a negative sign multiplied by a negative sign coming from delta y, and the rest is positive. That means the work is positive. And indeed, that's what we have. If an object is traveling downward, the work of gravity is positive, because the direction of the displacement is in the same direction of the gravitational force. So this formula is consistent, is nice, and we made sure that everything is fine. Now we can use this formula in order to define the potential energy of gravity, due to gravitational force, which is a conservative force. We use, in this sense, the definition delta U is equal to the negative of the work, in which case we arrive at the formula that the difference in the potential energy of the system consisting of an object plus Earth is equal to minus Wg, the work done by gravity on the object, which is equal to m times g times delta y. So this is the change in the potential energy due to the force of interaction, which is the gravitational force between the two parts of the system, which is object, Earth. So if delta y is positive, that means if the object is going up, the potential energy of the system increases. And if delta y is negative, that means if the object is going down, if the two objects are getting closer to each other, that means, then the potential energy decreases, it drops down. And that's also a logical consequence, because the conservative force conserves energy. If the particle is going up, then the kinetic energy of the particle is reduced. The kinetic energy of Earth, which is the second part of the system, does not change by this interaction. The interaction is so small relative to the mass of the Earth. So it does not change. The only change, we can see it in the motion of the object, which is a small mass relative to Earth. So as the particle travels up, it loses kinetic energy. That means the kinetic energy is transferred into potential energy. That means the potential energy of the system must grow. And that's exactly what we have. If delta y is positive, the particle is going up, then the change in the potential energy is positive. The change in potential energy is positive means the potential energy of the system increases. And vice versa. If the two objects get closer to each other, that means the particle goes down, then delta y is negative, and consequently the object, as it falls, it gains kinetic energy. But where does it gain this kinetic energy from? Because the potential energy of the system is reduced and it is switched into kinetic energy, and thus the change in potential energy is negative in this sense, which means the potential energy of the system goes down, it decreases, and it is transferred into kinetic energy. So again, this result is a consistent result. Now, in order to define the potential energy as a function, we have to decide upon a reference frame relative to which we measure the energy, because what we have learned is to find how do we find the difference in energy between an initial configuration and a final configuration. But in order to find the energy, the potential energy at a given configuration or at a given arrangement of the system, we have to define where do we have the potential energy equals zero, the reference relative to which we measure the potential energy. Of course, that reference, we can choose it anywhere. Any configuration we want, we can choose it and call it potential zero, like the Cartesian coordinate system, which we use to measure positions, for example. You can select any system you want. But as a convenient choice, we can always consider the initial position of the particle as it moves. We can consider it as the origin, our origin, with y equals 0. At this configuration, where the particle is arranged relative to Earth, of course the system has a potential energy because it is interacting. The Earth and the particle is interacting at any configuration they have, and they have an intrinsic potential energy between them due to their interaction. But we can always assign this energy, because it's a constant energy, we can call it 0, eliminating it from all of our treatment in the future. So at the initial position of the particle, we can call the initial position 0, starting from the origin, that means, and we can assign an initial potential energy of 0 to the system at this configuration, at this position of the particle. And thus, we obtain u, delta u is u minus u initial, which is simply u. We have decided to choose u initial is equal to 0, is equal to mg delta y. Delta y is y final, which is y minus y initial. And also we have decided to take y initial as 0. And thus we arrive at a definition of the potential energy of the system, which depends on the altitude of the object relative to its initial position. So the potential energy due to gravity, U, is equal to mg times y, where y is measured relative to the initial position of the object. And again, the initial potential energy Ui is taken to be 0. The other example of the conservative forces is the elastic force or the spring force. The elastic force applied by the spring, which obeys Hooke's law, is a conservative force. And we have calculated the work done by such a force previously. We found that the work done is 1/2 k x initial square minus 1/2 k x final square. And in order to evaluate the change in potential energy of the system as an object moves from an initial position where it's attached to the free end of the spring to a final position, we use the definition delta U is equal to the negative of the work done by the force. And this is simply equal to 1/2 k x final square minus 1/2 k x initial square. That is again the change in potential energy as an object attached to the free end of a spring moves from an initial position to a final position. In order to calculate the potential energy function for the elastic force, the elastic energy, that means we have also to take into consideration a point where we consider as a reference point, where it has 0 displacement, and at the same time we can assign to it a 0 potential energy. This will give us a tool or a means of calculating the potential energy function at any position of the particle relative to the reference position. In a spring, we consider that the reference position is the equilibrium situation of the system, where the spring is not stretched and it's not compressed either. It's in the relaxed position. That position, we call it x sub I, which is, we assume that the system starts from this initial position. We call it 0. And there is an internal energy of the system at this configuration, of course, but we can, since it's a constant, it doesn't change. This at this particular configuration, the energy doesn't change. We can always give it any constant value, and it's always convenient to consider that value to be 0. So we consider U sub initial is equal to 0 as a convenient choice. And thus, we obtain a functional for the potential energy U of x is equal to 1/2 k x square. So we can say the potential energy stored in an object spring system is equal to 1/2 k x square, where k is the spring constant and x is the stretch or the compression of the spring from the relaxed position. Now, this leads us to the definition of the mechanical energy of the system in order to arrive at the basic principle that we are after, which is the conservation of mechanical energy. Mechanical energy, which is written as E of the system, is defined as the summation of the potential energy plus the kinetic energy of the system. Since we have developed the formula for the work done by a conservative force and its relation to the change in kinetic energy and also its relation to the change in potential energy, then we can arrive at the relation where delta U is equal to minus the work, but the work is equal to the change in kinetic energy. Thus, delta U is equal to minus delta K. And this is the case where we have a conservative force, because you remember that if we have a conservative force, then we can associate a change in potential energy or a potential energy functional with it. And in this case, if we have a conservative force acting on the system, then from this previous relation, we get delta U plus delta K, which is equal to the change in total mechanical energy, is equal to 0. This result or this statement is known as the principle of conservation of mechanical energy. And this is a very essential conservation principle that we can use in many phenomena in our everyday life. This principle allows us to solve problems which could be very difficult, extremely difficult to solve by only using Newton's laws of motion. So, for example, let's look at this problem where we have a path which is not convenient to analyze at all, and we have an object that is rolling or that is sliding across this path. It would be extremely difficult indeed to use Newton's laws of motion to analyze this motion and to obtain the velocities and the other unknowns that we are after. So in this case, in a problem like this, we can always use the conservation of energy if we make sure that we do not have non-conservative forces acting on the system. Meaning, if all the forces acting on the system are all conservative, if we don't have friction, for example. If we have friction, then the story is different. We have dissipative forces and we lose energy that we will discuss in a little while. Non-conservative forces act also and do work. In order to touch on the effect of non-conservative forces, we have to make a definition. We call W sub C the work done by conservative forces, which we have discussed so far, and we call W sub NC the work done by non-conservative forces. Thus, if we have a collection of forces acting on a system, if some of these forces are conservative and some of these forces are non-conservative, then the total work done by all the external forces on the system would equal the change in its kinetic energy. That means W sub C, the work done by conservative forces, plus W sub NC, the work done by non-conservative forces, is equal to the change in kinetic energy. And in this sense, if we substitute for W sub C minus delta U, because this is the definition, delta U is equal to minus the work done by conservative forces. So if instead of the work done by conservative forces we substitute minus the change in potential energy and rearrange this equation, we will arrive at the result W, the work done by non-conservative forces, is equal to the change in kinetic energy plus the change in potential energy, and this change in kinetic energy plus change in potential energy is simply the change in the total mechanical energy, which means that if non-conservative forces are acting on an object, it will change its total mechanical energy, and the total mechanical energy is not conserved anymore due to the work done by non-conservative forces. Work done by friction, for example, is always equal to minus the force of kinetic friction times the displacement. We take into consideration the kinetic friction because, of course, if the particle is not moving or if the object is not moving, then there is no work done. So if we are talking about work, that means we are considering the object while it is moving, in which case the kinetic friction is working on it. And since the kinetic friction is always working on the opposite direction to the motion or to the displacement, then there is an angle of 180 degrees between the force and the displacement, in which case cosine phi is equal to -1, and thus the work done by friction is always minus F sub k times the distance traveled by the object. This is a negative work. This is a negative work which transfers energy from the system, or kinetic energy in particular, if the object is moving on a horizontal surface, then the work of friction is converting kinetic energy into thermal energy, assuming that the potential energy is not changing. Now we can say that the mechanical energy is not conserved. The mechanical energy is not conserved in the presence of non-conservative forces. But if we take into consideration the fact that the work of the non-conservative forces goes into another type of energy, thermal energy, which is a change in an internal energy of the system as its temperature goes up, if we take that into consideration, then we will arrive at the conclusion that the change in the internal energy of the system plus the change in the mechanical energy of the system, which is delta U plus delta K, should be 0, which means that if the mechanical energy of the system is reduced, that means the internal energy of the system is increased by adding heat to it, and vice versa. And this is the principle of the conservation of total energy, both mechanical and otherwise. So total energy, if we take into consideration all the elements that act and all the forces that act in the universe, we will arrive at the basic conclusion that the total energy of all types in the universe is conserved. And at this point, I would like to finish this lecture and thank you for your attention.